Welcome to my talk on a novel higher-order Weisfeiler-Lehman graph convolution. My name is Clemens Damke, and this is a joint work with Vitalik Melnikov and Eike Hüllermeier. Let's start off by considering the problem of graph neural network-based graph embeddings. There we are given a couple of graphs, and our goal is to embed those graphs in some vector space. This could, for example, allow us to differentiate between toxic and non-toxic molecules by finding some separating hyperplane in our embedding space. Now, the fundamental question we'll tackle now is which graph properties can we in general encode in our embedding space? To answer that question, we'll take a closer look at the inner workings of those graph neural networks. In particular, we'll take a closer look at the so-called Weisfeiler-Lehman graph convolution concept. To understand what this is all about, we'll take a quick detour into theory now and consider the so-called Weisfeiler-Lehman graph colorings. In particular, they are one-dimensional variant, where the core idea is to characterize graphs via multisets of so-called colors. For example, if we are given such a graph, we start off by coloring all the vertices of this graph with some initial color, for example A. What we then do is iteratively refine these colors by looking at the current color and the colors of all the neighbors of each vertex to determine some new refined color for all vertices. And this process is repeated until we reach some kind of stable coloring. The resulting multiset of vertex colors is then used as a vertex order invariant characterization of our graph. Now the question is, of course, what does this have to do with graph neural networks and graph convolutions? Well, recent results have shown that essentially current graph neural networks are just continuous relaxations of this color refinement scheme that I just described. So in the GNN setting, we consider continuous vertex feature vectors, which correspond to the discrete colors in the original Weisfeiler-Lehman setting. And our refinement steps in the GNN setting correspond to graph convolutions, which produce continuous convolved feature vectors. In the end, after applying a sequence of convolution layers, we obtain a set of vertex feature vectors, which we could then, for example, aggregate to obtain a graph vector embedding. Now, due to the relation between graph neural networks and the one-dimensional Weisfeiler-Lehman algorithm, a natural question is, what are the limitations of this one-dimensional coloring scheme? Well, one limitation is that we are in fact unable to distinguish between graphs of the same size and degree. So these two non-isomorphic graphs, for example, would look to the one-dimensional coloring scheme at least to be completely identical, since they both map to the same multiset of colors. So from the GNN perspective, this would mean that we are essentially forced to always map these two graphs to exactly the same point in space. Now, this limitation alone might not seem so bad, since we don't typically deal with datasets that just contain regular graphs of the same size and degree. However, there's also a second limitation of the one-dimensional coloring scheme, and that is that we are unable to detect cycles. And that is much more interesting from a practical perspective in many situations, since, for example, molecules often contain carbon rings, or social networks have the important clustering coefficient metric, and both of these properties heavily depend on the ability to be able to detect cycles in graphs. And this is something that cannot be done using a one-dimensional coloring scheme. Now, how could we overcome these limitations? Well, what we just looked at was the one-dimensional Weisfeiler-Lehman coloring scheme, and this already implies that there are also higher dimensional generalizations of this scheme. For example, in the two-dimensional setting, what we would do is color pairs of vertices instead of individual vertices, and consequently in the three-dimensional variant, we would consider triples of vertices to which we assign colors. The general rule here is that the higher our dimensionality k goes, the higher the discriminative power gets, but at the downside that our runtime cost also goes up exponentially. So there's a kind of trade-off here, and what we propose is that the two-dimensional variant is a particularly interesting balance between power and cost. So let's look a bit closer at that now. As just mentioned, in the two-dimensional coloring scheme, we consider pairs of vertices to which we assign colors. Now, by definition, we say that the neighborhood of such a vertex pair is the set of all length 2 paths between the two vertices of our pair. Now, the fact that we incorporate path information into our neighborhoods turns out to be crucial to exceed the limitations of the one-dimensional coloring scheme. More specifically, it turns out that by essentially stitching together these paths that we have as part of our neighbors, we are able to detect cycles of up to length 7 in any given graph. So for example, here we would be able to tell just from the two-dimensional coloring that this graph contains 6 cycles and that this graph contains 2 3 cycles. One natural consequence of this is that we are able to distinguish, in fact, many regular graphs that are out there. So both of the limitations of the one-dimensional coloring scheme that we saw before don't apply in general to the two-dimensional coloring scheme. The downside of these advantages are that we have to consider a lot more vertex pairs for each refinement step. Secondly, the number of neighbors per pair turns out to be linear in the number of vertices in our graph. The reason for this is that we don't define the neighborhood of a pair of vertices as just the length to paths that actually exist in our graph between our two vertices, but as all the potential paths between our pair. What this means is that, for example, this green neighbor here would also be a neighbor between v1 and v2, even though this path actually doesn't exist in our graph. Due to this definition, what we get overall is a cubic time complexity for a single refinement step. This quickly becomes infeasible for many real-world datasets that consist of large graphs, so we need some kind of simplification. To reduce the time complexity, what we propose is to utilize the fact that many real-world graphs are in fact rather sparse. So the size of their edge set turns out to be often linear in the number of vertices of that graph. Now, to utilize sparsity, we propose that one could, instead of considering all the potential edges in our graph, only look at a subset of those edges. In the most extreme case, only the edges that actually exist in our graph. The advantage of doing this is that we in fact then obtain a runtime which is linear in the number of vertices. However, this comes with the downside that we actually lose very important information, since it turns out that these hidden edges are actually used to carry information that is necessary to detect cycles, for example. To trade off between runtime and the full expressive power of the two-dimensional Weisfeiler-Lehman colorings, we introduce the so-called neighborhood radius, which allows us to at least consider some of the non-existent edges. This still gives us a runtime which is linear in the number of vertices without losing much of the expressive power of the full method. For example, if the neighborhood radius is 2, we would consider all the non-existent edges between edges that are 2 hops apart. So how does our proposed novel higher-order Weisfeiler-Lehman graph convolution now actually look like? Well, inspired by the two-dimensional Weisfeiler-Lehman coloring scheme that we just looked at, in the convolution setting what we do is we assign feature vectors to all the edges in our graph. To convolve the feature vector of an edge, we combine its current feature vector with the feature vectors of the edges that lie along all length 2 paths between its incident vertices. How exactly this type of feature vector combination works won't be covered here. We'll instead now focus at the formal properties of our proposed convolution operator. One foundational theorem we have shown for our proposed two-dimensional operator is that for any given one-dimensionally bounded graph neural network, you will be able to construct a two-dimensional graph neural network that produces exactly the same graph embeddings for any given graph. This essentially means that we don't lose anything by going to a higher dimension. Of course, our motivation was not to just simulate the existing one-dimensional approaches. There would be no point in that. We actually wanted to go beyond them. So we also showed a second result, which shows that we are indeed able to distinguish graphs that are indistinguishable by the existing one-dimensional approaches. Overall, we can therefore conclude that our proposed two-dimensional graph neural network family is a proper superset of the existing one-dimensional approaches. To illustrate that result empirically, we have evaluated our proposed model on the so-called triangle detection problem, where the goal for the learner is to find so-called unicolored triangles which determine the class of a given graph. Since this is inherently a cycle detection problem, we would assume that our proposed two-dimensional approach performs better than the existing one-dimensional approaches. And this is in fact what we observe. This GNN architecture here, for example, is a state-of-the-art one-dimensionally bounded graph neural network, and as you can see here, its generalization performance is significantly worse than that of our two-dimensional approach. So this really illustrates also empirically that two-dimensional graph neural networks have a unique advantage over the existing one-dimensional approaches. So what are the key takeaways here? Well, we started off by looking at the fact that current graph neural network architectures are bounded by the one-dimensional Weisfeiler-Lehman algorithm and are therefore unable to distinguish between regular graphs and are also unable to detect cycles in graphs. To overcome these limitations, we therefore proposed the novel two-dimensional Weisfeiler-Lehman graph neural network architecture, which is provably more powerful than these existing architectures, which was also observed empirically. Now, in the next step, we want to evaluate our model on a broad range of real-world graph datasets to evaluate where our theoretical advantages also translate into practical advantages. One such domain could be, for example, that of code analysis, where it could be helpful to be able to detect things like loops or recursion in control flow graphs. And with that outlook, I'd like to thank you all for your attention.